Hello everyone, and welcome back to Tech Adventure. Hope you're doing great and staying sharp in your journey of software development, embedded systems, and interview preparation. In our previous videos, we explored the top 50 real-world C and C++ interview questions, the solid principles, and common design patterns. If you missed those, be sure to check them out. They lay a solid foundation for what's coming next. Today we start a new deep dive series on microcontrollers and their peripherals, exploring key hardware blocks, real-world applications, and common interview questions. Our first focus is the ADC, the analog-to-digital converter at the heart of almost every embedded system. Let's dive in, from core concepts to advanced ADC questions. Let's dive in.
Welcome to the Deep Dive. Today we're plunging into a piece of technology that's absolutely everywhere, yet often completely invisible. The analog-to-digital converter, or ADC. Think about it. Our world is inherently smooth, continuous, a light dimming, a temperature subtly shifting, the rich ebb and flow of sound waves. But the digital devices we use every day, especially our microcontrollers, they speak a different language entirely. It's the crisp, precise language of ones and zeros.
And bridging that fundamental chasm between the messy, real world and the precise digital brain of our devices. That's exactly where our star of today's deep dive comes in.
Right. So our mission today is to demystify ADCs. We'll explore what they are, why they're so utterly crucial, how they fundamentally work their magic, and even pull back the curtain on some advanced techniques engineers use to squeeze every last bit of performance out of them. Great. So let's unpack this right away. Why do we even need ADCs? Can't our devices just understand the real world directly?
Well, that's the core challenge, isn't it? The real world, like you said, it's analog. Imagine a light dimmer switch. You can set it to any brightness level between off and maximum, smoothly. But our digital devices, they're more like a simple on-off light switch representing those binary ones and zeros.
It's just on or off, exactly.
And most signals we actually interact with temperature, pressure, sound, velocity, they're all analog. Even when a sensor, what we technically call a transducer, converts something like pressure into an electrical signal, well, the electrical signal often remains analog.
Okay, so if we've got this analog electrical signal, what's the problem with just keeping it that way? Why the need to go digital?
The fundamental insight here is about noise and processing. While the world is analog, the digital realm offers this almost magical immunity to noise. And it's incredible.
So whenever your device needs to sense the physical world.
Yep, the ADC is the unsung hero making that translation happen.
Could you give us some everyday examples? Where is this silent translation happening all around us?
Absolutely. Think about streaming music on your smartphone. The digital audio file gets converted by a DC, a digital to analog converter, into an electrical signal your headphones can play.
Okay, the reverse process.
Right. And conversely, when you're talking into your phone, your voice is an analog sound wave. The microphone converts that into an electrical signal, which an ADC then digitizes for transmission. Then at the other end, the process reverses with another DC.
Because we're constantly using them.
We're interacting with ADCs and DACs constantly, often without even realizing it.
It's incredible how often these conversions are happening without us even noticing. Okay, so we know these invisible translators are essential. But how do they actually perform their magic? How does an ADC take this world of continuous signals and neatly package them into discrete digital steps?
Well, the process generally boils down to three core steps: sampling, quantization, and encoding.
Okay.
First step is sampling. Imagine taking snapshots of a moving object. Sampling means taking discrete measurements of the analog signal at specific moments in time. The sampling rate, or sampling frequency, tells you how many of these snapshots the ADC takes per second. It's typically expressed in samples per second, SPS, or sometimes hertz.
And why is that snapshot rate so critical? What happens if you don't take enough pictures, so to speak?
If you sample too slowly, you'll completely miss rapid changes in the signal. It's like watching a strobe light. And when you try to reconstruct it later, it just won't look anything like the original.
Right.
The Nyquist rule is fundamental here. It basically says to accurately capture a signal of a certain frequency, F, You need to sample at least twice that frequency, 2F.
Ah, the Nyquist frequency.
Exactly. If your sampling rate is too low, you get this weird effect called aliasing. Higher frequencies actually appear as lower frequencies in your digitized signal.
Like the wagon wheels in old movies appearing to spin backward.
That's the classic example. To prevent this, we use anti-aliasing filters. They're usually low-pass filters placed right before the ADC to chop off those unwanted high-frequency components before they can cause trouble.
That makes perfect sense. But what if the analog voltage itself changes while the ADC is in the middle of its conversion process? That seems like it could mess things up.
You've hit on a really critical point. Analog voltages can absolutely drift or change during the conversion itself. And that conversion might take dozens, maybe even hundreds of clock cycles depending on the ADC type.
So how do you get an accurate snapshot?
To ensure accuracy, most ADCs use something called a sample and hold circuit. This circuit takes a very quick, precise snapshot of the input voltage and then, crucially, holds that voltage steady for the entire duration of the conversion. It ensures the ADC core has a stable value to work with, even if the input changes slightly afterwards.
Okay, so sampling grabs a stable value. What's next?
After sampling, the next step is quantization. This is where the magic of digital happens. The ADC assigns a specific numerical value from a limited set of possibilities to that sampled analog voltage. The resolution of the ADC tells you how finely it can discriminate between different voltages, how many steps it has.
And this is where bits come in, right? Like when we hear about an 8-bit or a 16-bit ADC.
Exactly. Resolution is expressed in bits, commonly 8, 10, 12, 16, or even 24 or 32 bits for really high-precision scientific or audio applications. An n-bit ADC divides the total input voltage range into 2 to the power of n discrete steps or levels.
So a 10-bit ADC.
Right. A 10-bit ADC quantizes the signal into 210, which is 124 unique levels.
How does that actually translate to real-world sensitivity? Like how small voltage change can it actually detect?
Good question. Let's take that 10-bit ADC and say it has a reference voltage of 3.3 volts.
Yeah.
It can resolve voltage steps of about 3.3 divided by 1124, which is roughly 0.00032 volts or 3.2 millivolts. Now, compare that to a 16-bit ADC using the same 3.3V reference. 16 bits is 216, or 65,536 levels. So 3.3 volts divided by 65,536, that means it can discern steps as tiny as 100,005 volts, or 50 microvolts.
Wow, that's a massive difference in precision.
Huge difference. Think of it like video resolution. A high-res video, like 1080p or 4K, shows much finer detail than a low-res one, like 240p, which looks blocky, pixelated. More bits in an ADC means a more accurate, less pixelated conversion of your analog signal.
So more bits equals more detail, just like more pixels. But does this stepping process, this quantization, introduce any unavoidable errors?
It does, unfortunately. It introduces what's called quantization error. It's an inherent uncertainty, sort of a rounding error, typically around plus or minus half of the smallest step size, which we call the LSB, or least significant bit.
LSB.
This error is intrinsic to the process of turning a smooth, continuous signal into discrete steps. You can reduce its relative impact by increasing the number of bits, or sometimes by carefully shifting the ADC's transfer function, but it's always fundamentally there.
All right. What about this reference voltage you mentioned? Ref.
Ref. Hugely important. The reference voltage defines the absolute voltage range the ADC can measure. The ADC essentially maps 0 volts input to a digital output of 0, and it maps the ref voltage to the highest possible digital code, which is 2n-1 for an n-bit ADC.
So for that 10-bit ADC with a 5-volt ref.
Right. It maps the 0 to 5 volt input range to digital values from 0 all the way up to 1023.
So if your sensor puts out, say, 6 volts, but your ref is set at 5 volts, that's a problem.
A very big problem. First, an input voltage significantly higher than ref could potentially damage the ADC input circuitry.
Ouch.
And second, even if it doesn't damage it, the ADC simply can't measure beyond ref. It'll just saturate, outputting the maximum value, 1023 in our example.
Plus,
the accuracy and stability of ref directly impacts the absolute accuracy of every single reading.
So a shaky reference means shaky readings.
Absolutely. If your ref fluctuates all your measurements will fluctuate accordingly, even if the actual input signal is perfectly stable. You could often use internal references built into the microcontroller, which are convenient. But for higher precision applications, engineers often supply a dedicated, highly stable, external reference voltage chip.
Makes sense.
And there's also a trade-off. While you might adjust ref to better match your sensor's output range, which can effectively change the voltage value of each step, remember, it also changes the ADC's overall conversion range. You might gain sensitivity in one area, but lose range overall.
Gotcha. Now, you mentioned microcontrollers often have ADCs built in. Do they usually handle just one sensor input?
Usually no. Most microcontrollers are designed to handle multiple analog inputs using a single internal ADC block. These different inputs are called channels. An 8-channel ADC, for instance, can be connected to 8 different sensors.
How does that work? Does it read them all at once?
Not usually. You typically tell the software which specific channel you want to convert before you start each reading. The microcontroller internally connects that chosen input pin to the ADC core.
And are there different ways these channels measure voltage, like different modes?
Yes, generally 2 main types. There are single-ended channels, which measure the voltage of one input pin relative to ground, 0V, that's most common. And then there are differential channels. These measure the voltage difference between 2 input pins.
Why would you use differential?
Differential inputs are fantastic in noisy environments. Because they measure the difference, any noise that affects both input wires equally gets canceled out. It's great for rejecting common mode noise.
Clever.
But yeah, typically a single ADC core can only perform one conversion at a time, whether single-ended or differential. You select a channel, convert, select the next, convert, and so on. Unless, that is, you have more specialized microcontroller with dual or simultaneous ADCs, which can sample multiple channels at the exact same instant.
Okay, let's try to put all these pieces together, maybe a simple real-world scenario.
Sure. Let's go back to that temperature sensor. Imagine it outputs 0 volts at 0 degrees Celsius and 5 volts at 100 degrees Celsius.
Yeah.
Nice linear output.
Okay.
And let's say we're using our 10-bit ADC again with a 5-volt reference for 5E. The digital output range is 0 to 1023. If the sensor is reading 50 degrees Celsius, it should output half the voltage range, so 2.5 volts.
Right in the middle.
Exactly. The ADC reads at 2.5 volts. Since 2.5V is exactly half of the 5V range, the ADC's digital output will be approximately half of its maximum count. So half of 1024 is 512. The ADC outputs a digital value 512.
And the microcontroller gets that 512.
And the software in the microcontroller knows, based on how we set it up, that 512 corresponds to 50 degrees Celsius. It does the simple math, ADC reading, max reading, temperature range plus offset. So 512, 20 degree 300 degrees dilation.
That really clarifies the whole translation process, from voltage to number to actual meaning. Okay, now that we understand that fundamental translation, here's where I think it gets really interesting for engineers. Beyond these core concepts like resolution and sampling rate, what other parameters do people grapple with when they're selecting or configuring an ADC for a specific job?
Yeah, this is where the nuances come in. We start looking deeper into things like conversion time, throughput, overall accuracy, noise sources, calibration options, and also the different operating modes the ADC can run in.
Let's start with conversion time. How fast can these things actually work?
Conversion time is simply how long it takes for one complete analog to digital conversion, start to finish. It's influenced by a few things. The ADC's internal clock speed, the number of internal clock cycles needed for each conversion step, which often depends on the ADC's architecture, and also whether you're using extra techniques like oversampling, which deliberately takes more time.
Is faster always better?
Not necessarily. Generally, a shorter conversion time allows for a higher maximum sampling rate, which is good for fast-changing signals. We call that higher throughput. But sometimes pushing for maximum speed might mean sacrificing a bit of resolution, or it might introduce more digital noise into the analog circuitry, potentially reducing accuracy. There are trade-offs.
Okay. And you mentioned accuracy and noise beyond just the quantization error. What else affects the readings?
Right. Real-world ADCs, sadly, aren't perfect. Beyond that inherent quantization error, Key error sources include things like thermal noise, just random voltage fluctuations caused by temperature. It adds fuzziness. And then there's systematic errors, like offset error and gain error.
Offsetting.
Yeah, offset error means that even with a perfect 0-volt input, the ADC might read a small positive or negative value instead of 0. And gain error means the slope of the ADC's response isn't quite right. So maybe at the maximum input voltage, ref, it doesn't quite reach the maximum digital output code, or maybe it reached it too soon.
Can you fix those?
Often, yes. Most modern microcontrollers provide ways to perform calibration. You might do a 1-point calibration, measuring a known 0 point, or a 2-point calibration, measuring 0 and a known full-scale point, to digitally calculate and remove these systematic offset and gain errors. And for random noise, like thermal noise, averaging multiple readings or applying digital filters can significantly improve the stability and consistency of your measurements.
You also mentioned different operating modes.
Yes, ADCs can operate in various modes, dictating how and when they perform conversions. Single conversion mode is basic. You trigger it, it converts once, then stops until triggered again. Continuous mode is useful. You trigger it once, and it just keeps converting back to back, constantly updating its output register with the latest value.
Non-stop readings.
Right. Scan mode is handy when you have multiple sensors connected to different channels. You can configure it to automatically cycle through a sequence of channels, maybe channel 1, then channel 3, then channel 5, converting each one in order.
Oh, neat.
And finally, and often most efficiently, you have interrupt mode or DMA mode. These allow the ADC to signal the CPU or transfer data directly to memory after a conversion is complete, without the CPU having to constantly check if it's done. This frees up the CPU enormously.
We'll definitely want to circle back to DMA later, but before that, what's fascinating here is that you mentioned different architectures. So there isn't just one internal blueprint for an ADC.
Not at all. They have very different internal personalities, we could say, optimized for different things.
Like what?
Well, take flash ADCs, also called direct conversion ADCs. These are the speed demons. They use a massive bank of comparators, one for almost every possible output level, essentially checking all possibilities in parallel. Incredibly fast.
What's the catch?
The catch is they need a lot of comparators, like 2-in-1 comparators for M bits. So for high resolution, the chips become physically large, consume a lot of power, and get very expensive. You find them in really high-speed stuff, like oscilloscopes or software-defined radio.
Okay, so flash is fast but pricey.
Yeah.
What's common in microcontrollers?
Arguably, the most common type you'll encounter in general-purpose microcontrollers, like STM32s or Arduinos, is the Successive Approximation Register ADC, or SAR ADC.
SAR, okay, how does that work?
A SAR ADC is clever. It works by making a series of educated guesses, like a binary search. It starts with its most significant bit, MSB. It internally generates a voltage halfway through the range using a DS and compares it to the input. Is the input higher or lower? Based on that, it sets the MSB to 1 or 0.
So it figures out the top half or bottom half first.
Exactly. Then it moves to the next bit, adjusts its internal DD to 14 or 34 of the range, depending on the first guess, compares again, and sets the second bit. It continues this process iteratively, comparing and adjusting bit by bit down to the least significant bit, LSB, zeroing in on the input voltage.
So it's applying 20 questions to find the voltage value.
That's a great analogy. And it's incredibly efficient. For an N-bit ADC, it typically takes just N clock cycles, plus maybe a few for overhead, to complete the conversion. This makes its conversion time very predictable and, importantly, independent of the actual input voltage value.
What are the pros and cons of SAR?
Pros: great balance of speed, resolution, and power consumption. Typical resolutions are 8 to 16 bits, maybe up to 20. Speeds can reach several megasamples per second. MSPS, maybe 2 to 5 MSPS commonly, some up to 10. They offer good accuracy, require relatively low power, are easy to integrate and use, and often have zero latency, meaning the data from the sample is ready right after that N-cycle conversion finishes.
Makes sense why they're so popular.
Yeah, they hit a sweet spot for a huge range of applications.
Are there others worth mentioning?
Sure, briefly. Tracking ADCs are similar to SAR, but instead of starting fresh each time, they have a counter that continuously adjusts up or down to follow the input signal. They can be very fast for slowly changing signals, but can sometimes have bit bobble, where the output flickers between adjacent values. And then there are slope or integrating ADCs. These actually measure time. They use an op-amp circuit called an integrator to charge a capacitor with the input current for a fixed time, and then measure how long it takes to discharge that capacitor using a known reference current.
Measuring time to measure voltage. Interesting.
Yeah, a common variation is the dual slope ADC, which integrates the input up and then integrates a reference voltage down. This makes them very good at rejecting noise and can achieve high resolution. But they are generally much slower than SAR or flash ADCs, and their accuracy can sometimes drift with temperature or time. You often find them in digital multimeters where speed isn't critical, but accuracy is.
Okay, that gives a good sense of the different flavors. You also mentioned something called step recovery time.
Yes, step recovery. That refers to how quickly an ADC's output can accurately settle to a new value after a large, sudden change, a step change in the analog input. If your signal makes very sharp jumps, you need an ADC with good step recovery performance to make sure it doesn't lag behind or give inaccurate readings during those transitions. It's important for dynamic signals.
Right, you don't want it to miss the jump.
Precisely.
So let's bring this down to earth. What does this all mean for someone actually building something? Needing to use an ADC in a real-world microcontroller, like a common one, say an STM32.
Okay, yeah, let's get practical. When you're configuring an ADC on a microcontroller like an STM32, there's a pretty structured approach. It involves getting the hardware connections right, setting up the ADC's internal parameters using software tools or code, and then writing the routines to actually trigger and read the conversions.
Step 1, the hardware. What's key there?
First, physically connecting your sensor output to the correct pin on the microcontroller. It has to be an ADC-capable pin. These are specific general-purpose input-output pins, GPIOs, that are internally connected to the ADC peripheral. You'll find these listed in the microcontroller's datasheet, like PA0 might be ADC1IN0.
Got it. Check the datasheet.
Absolutely. Then, crucially, that pin must be configured in its analog input mode. This disconnects the digital input-output buffers from that pin, preventing them from interfering with the sensitive analog signal.
No digital stuff messing with the analog signal.
Right. And you also need to make sure you have a stable analog reference voltage, ref plus A, applied to the correct pin. Often this is simply connected to the microcontroller's main power supply voltage, VDD, but sometimes you might use an external reference.
Okay, hardware sorted, then the software side.
Next comes the software configuration. Manufacturers provide tools to help with this complex setup. For STM32, the go-to tool is usually STM32CubeMX. It's a graphical tool. You visually enable the ADC peripheral you want to use, say ADC1. Then you click on the GPIO pin you connected your sensor to and set its mode to analog.
Nice and visual.
Yeah, it simplifies things a lot. Then, within the ADC settings in CubeMX, you configure all those parameters we discussed. You might choose the resolution, like a G12-bit. You'd likely disable scan conversion mode if you're only reading one channel for now. Maybe enable continuous conversion mode if you wanted to keep reading automatically. Set the trigger source to software start so your code initiates it. Specify data alignment, usually right aligned.
What about sampling time?
Yes, you'd also tune the sampling time. This controls how long the sample and hold circuit stays connected to the input pin before conversion starts. We'll talk more about the trade-offs there later, but you might pick a value like, say, 15 cycles or maybe 480 cycles. And you need to make sure your main peripheral clock, like the APB2 clock, feeding the ADC is fast enough, maybe 84 megahertz or more, depending on the specific STM32 and desired speed, and configure the ADC clock prescaler appropriately.
And you can set up DMA here too.
Optionally, yes. In CubeMX, you can enable DMA requests for the ADC's received data, which sets things up for more advanced, efficient data transfer later.
Okay, so CubeMX sets it all up. Then what?
Then you generate the code. CubeMX writes the low-level initialization code for you, typically in a function like mxADC1INIT. This generated code sets up the ADC's internal configuration registers based on your choices: the handler structure, clock prescaler, resolution, continuous mode setting, data alignment, number of conversions, DMA settings if enabled. And then it configures the specific channel settings, like which channel it is, its rank in the sequence, if scanning, and that crucial sampling time.
So the setup is mostly automated. How do you actually get a reading in your code?
After that initialization runs, you can start conversions. The simplest way, especially when you're starting out, is using polling mode. In your main code loop, you typically call a function like ADT start to kick off a conversion.
Start the engine.
Yep. Then you call ADC poll for conversion. This function basically sits there and waits, repeatedly checking a status flag inside the ADC until the conversion is finished.
It just hangs out until it's done.
Pretty much. Once poll for conversion returns, meaning the ADC is done, you call HAEDC get value to retrieve the digital result, that number, maybe 0 to 4, 095 for 12-bit.
Mm-hmm.
And then if you're in single conversion mode, you might call HADC stop.
Okay, that sounds straightforward enough for maybe one reading here and there, but it also sounds like the CPU is just waiting around doing nothing useful while polling.
That's exactly the drawback. In polling mode, the CPU is stuck in that poll for conversion loop, busy waiting. It's burning clock cycles, consuming power, and effectively blocked from doing anything else.
Not very efficient.
Not at all. Especially if you need to read multiple channels frequently or sample at high rates. The CPU gets completely bogged down just waiting for the ADC.
So what's the better way? You mentioned interrupts.
Exactly. A far more efficient approach is using interrupt mode. The setup is similar, but instead of starting with ATLD statesar, you use a function like AATC started. The IT stands for interrupt. This tells the ADC to start converting. But crucially, the CPU doesn't wait. It immediately continues executing other code in your application's main loop or goes to sleep if there's nothing else to do.
So the CPU is free. What happens when the ADC finishes?
When the ADC completes its conversion, it automatically sets an internal flag and generates an interrupt signal. The microcontroller's interrupt controller hardware sees this signal and automatically redirects the CPU to execute a specific function and interrupt service routine, ISR. In the context of the HAL library often used with STM32, this ISR then typically calls a predefined callback function, like HALADC convc callback.
A callback function.
Yes, this is a function that you write in your code. Inside this convcpl key callback function, you know a conversion is just finished, so you can safely call HALDC get value to get the result and process it. Then the callback function finishes, and the CPU resumes whatever it was doing before the interrupt occurred.
What's really cool here is that this completely frees the CPU. It only gets involved for that brief moment when data is actually ready.
Absolutely. This interrupt-driven approach is vastly more efficient than polling. It liberates the CPU from busy waiting. It lets you handle ADC data asynchronously dealing with it when it arrives, which dramatically improves the overall responsiveness and efficiency of your whole microcontroller system. You can do many other things while the ADC works in the background.
Okay, that makes a lot of sense for efficient operation. Let's connect this now into the bigger picture again. We've covered the fundamentals, different types, even how to get an ADC basically working with polling or interrupts. But how do engineers push beyond these basic capabilities? How do they get even better results, maybe squeezing out more resolution than the ADC technically has, or handling data even more efficiently?
Now we're getting into the advanced stuff. This is where techniques like oversampling, digital filtering, and really leveraging direct memory access, DMA, come into play. These strategies essentially allow you to cleverly trade off things like processing time or the effective sample rate to gain benefits like higher effective resolution, reduced noise, or dramatically lowering the burden on your main CPU.
Okay, let's break those down. You mentioned improving resolution first, using oversampling.
Right. Oversampling is a fascinating technique. It's a way to effectively boost an ADC's native resolution using software processing. The core idea is, instead of taking just one reading from your analog sensor, you take multiple samples, let's say N samples of the exact same analog channel, one right after the other, as quickly as possible.
Okay, lots of readings of the same thing.
Yep. Then you take all N of those raw digital readings, add them all together to get a big sum, and then you average them. The averaging is typically done very efficiently by just right-shifting the accumulated sum in binary.
Shifting bits to divide. Clever. How much can you actually gain in terms of resolution by doing this? Is it magic?
It feels a bit like magic, but it's based on statistics and noise.
Yeah.
The rule of thumb is that for every fourfold increase in the number of samples you take, you gain 1 effective bit of resolution.
4 times the samples for 1 extra bit.
That's right. Because noise is random, averaging tends to cancel it out, and the process effectively gives you finer steps between the original ADC levels. So to gain 1 extra bit, which requires 41 samples, you sum 4 samples and right shift by 1 bit, divide by 2 technically, but the math works out to gain 1 bit. To gain 2 extra bits, requiring 42 equals 16 samples, you sum 16 samples and right shift the result by 2 bits.
So if I have a 12-bit ADC and want, say, 14-bit effective resolution,
you'd need 2 extra bits, so you'd take 16 samples, 4 squared. You'd loop 16 times, trigger the ADC, wait for it, maybe using interrupts for polling, get the 12-bit value, add it to an accumulator, which needs to be wide enough, like 32 bits, to avoid overflow. After collecting all 16 samples, you take that final sum and right shift it by 2 bits. Voila, you have a 14-bit result.
That's really neat. Trading speed for precision.
Exactly. You're taking 16 times longer to get 1 reading, but that reading has potentially 4 times the resolution.
And you mentioned digital filtering alongside this.
Yes. Digital filtering techniques are often used in conjunction with, or sometimes instead of, simple averaging from oversampling. They help further refine the signal and reduce noise. A moving average filter is very common and conceptually simple. You keep a buffer, like an array, of the last m readings. Your filtered output is simply the average of all the values currently in that buffer. As a new reading comes in, it replaces the oldest one in the buffer, and you recalculate the average.
So it smooths things out over the last m samples.
Precisely. It's great for smoothing out random noise spikes. The bigger m is, the smoother the output, but the downside is it introduces more delay, or lag, in reacting to real changes in the signal. Another popular one is an exponential filter, sometimes called an IIR, infinite impulse response filter. This calculates the new output based on a weighted average of the new incoming sample and the previous filtered output. It looks something like new output alpha new sample plus 1 alpha old output. That alpha value acts like a speed or smoothness control. A smaller alpha gives more smoothing but slower response.
More advanced options too, I assume.
Well, yeah. For more specific noise problems, engineers might use more complex filters like FIR, finite impulse response, or CIC, cascaded integrator quorum filters, especially in digital signal processing applications, to reject specific frequency bands of noise.
Okay, so oversampling and filtering help with resolution and noise. What about that trade-off between speed and accuracy you mentioned earlier related to sampling time?
Right. Let's revisit sampling time and the ADC clock prescaler. These are key tuning parameters. Remember that sample and hold capacitor inside the ADC? It needs time to charge up fully to match the voltage coming from your sensor. The sampling time setting directly controls how long the ADC's input is connected to that capacitor before the actual conversion begins. It's often measured in ADC clock cycles.
What's the practical trade-off when setting this time? Short versus long?
Okay, a short sampling time, maybe just 3 or 15 ADC clock cycles, allows for the fastest possible conversions, maximum throughput. But it puts a big demand on your sensor circuit. Your sensor needs to have a very low output impedance, meaning it can supply current quickly enough to charge that tiny sample and hold capacitor in that very short time.
And if it can't?
If your sensor has a high output impedance, like many simple voltage dividers or some types of sensors, a short sampling time won't be long enough for the capacitor voltage to accurately reach the sensor's voltage. Your readings will be wrong, often lower than they should be. Short times can also sometimes make the reading more susceptible to noise.
So longer, safer.
Generally, yes, for accuracy. A long sampling time, maybe 240 or 480 cycles, gives that capacitor plenty of time to fully settle to the sensor's voltage, even if the sensor has high impedance. This provides the best possible accuracy. The obvious trade-off is that it makes each conversion take significantly longer, reducing your maximum sample rate.
So it depends on the sensor and how fast you need to read it.
Exactly. If you have a high impedance sensor, you must use a longer sampling time. If you have a low impedance source, maybe your sensor goes through an op-amp buffer first and needs speed, you can use a shorter time. A medium setting often provides a reasonable balance.
And the clock prescaler, how does that fit in?
The ADC needs its own clock to time its internal operations, like those end steps in a SAR converter. This ADC clock is usually derived from the main microcontroller peripheral clock, like APB2 clock on an STM32, by dividing it down using a clock prescaler. You might divide the main clock by 2, 4, 6, 8, etc.
Faster clock, faster conversion.
Yes, a faster ADC clock generally reduces the overall conversion time, since sampling time and conversion steps are measured in these clock cycles. However, running the ADC clock too fast can sometimes introduce more digital switching noise back into the sensitive analog parts of the chip, potentially degrading accuracy slightly. Conversely, a slower ADC clock, using a larger prescaler value, usually gives cleaner, more stable results, especially when combined with longer sampling times. But again, it slows down the maximum throughput.
So it's another balancing act. How do engineers typically approach this tuning?
It's about understanding the goals. If maximum resolution is key, you'd likely use oversampling and digital filtering, accept the slower effective sample rate, possibly use a longer sampling time for stability, and maybe a moderate prescaler. If maximum speed is paramount, you'd use the shortest sampling time your source impedance allows, maybe skip oversampling, and use the fastest possible ADC clock, smallest prescaler, that still meets the datasheet limits and gives acceptable noise.
What if you need both speed and accuracy with a tricky sensor?
That's often where external circuitry comes in. A common solution is to put an operational amplifier, op-amp, configured as a voltage follower, a buffer, between the high impedance sensor and the ADC input. The op-amp has a very high input impedance, so it doesn't load the sensor, and a very low output impedance, perfectly capable of driving the ADC's sample and hold capacitor quickly.
So the buffer solves the impedance problem.
Exactly. It lets you use a short sampling time for speed while still getting accurate readings from your high impedance sensor. Best of both worlds, at the cost of an extra component.
Okay, this tuning makes sense. Now let's talk about the efficiency elephant in the room. DMA. You said it was a game changer.
Oh, absolutely. Direct memory access, or DMA, is incredibly powerful for handling ADC data, especially when you need continuous sampling or high data rates. Remember, DMA is a dedicated hardware unit inside the microcontroller. Think of it as a specialized coprocessor just for moving data around. Its job is to transfer data directly between peripherals, like the ADC, and memory, RAM, completely bypassing the main CPU.
No CPU involvement at all.
Well, the CPU needs to set it up initially, tell the DMA controller where the data is coming from, the ADC's data register, where it should go in RAM, a buffer array, how many data points to transfer, and how the transfer should work, AG circular buffer mode. But once you start it, the DMA handles the actual data transfers entirely on its own, in the background, whenever the ADC signals that has new data ready.
So what's the big advantage compared to using interrupts? Interrupts already seemed pretty efficient.
Interrupts are good, much better than polling. But even with interrupts, the CPU still has to wake up for every single conversion, execute the callback function, read the ADC value from its register, and store it somewhere in memory.
Okay, still some CPU work per sample.
Right. If you're sampling very fast or scanning multiple channels, the CPU can end up spending a significant amount of time just servicing these ADC interrupts, reading and storing data. DMA eliminates almost all of that CPU overhead for the data transfer itself. The ADC finishes a conversion, signals the DMA controller directly, and the DMA hardware just moves the data from the ADC register straight into your RAM buffer. The CPU doesn't even need to know it happened until maybe the whole buffer is full.
Wow, so the CPU is truly free to do other things.
Or even go into low-power sleep modes between processing chunks of data. DMA is fantastic for efficiency and power saving.
How does this tie into oversampling? You mentioned combining them.
Yes. Combining DMA with oversampling is a really elegant and efficient approach, especially for getting high-resolution readings from slower sensors, like temperature or pressure sensors. Remember, for oversampling, we need to collect many raw samples, like 16 for a 2-bit gain. Doing this with interrupts means the CPU wakes up 16 times just to grab those samples before it can even calculate the final average result.
Lots of little interruptions.
Yeah. But with DMA, you can configure the DMA controller to automatically collect all 16, or however many you need, raw samples from the ADC and place them sequentially into a buffer in RAM. The DMA can trigger an interrupt only after it has collected all 16 samples.
Ah, so only one interrupt for the whole batch.
Exactly. The CPU wakes up just once, finds all 16 raw samples waiting neatly in the RAM buffer, runs a quick loop to sum them up, performs the right shift to get the high-resolution average, and then it's done. Much, much less CPU overhead.
That sounds incredibly efficient for precision measurements.
It is. It's the perfect way to trade off that raw sample rate, because you're collecting many samples for one result, for significantly enhanced resolution and noise reduction, all while keeping the CPU load extremely low.
What's the typical flow or setup for DMA-based oversampling?
Okay, first you decide your oversampling factor, say 16 for that 2-bit gain. So oversample count in 16. Then in your code, you allocate a buffer in RAM to hold these raw samples, something like ON16 added a buffer oversample count. You also need a variable to store the final high-resolution result, maybe volatile ON16 added res value.
Got the storage ready?
Then you configure the ADC itself. You typically set it for continuous conversion mode, so it just keeps sampling back to back. And importantly, you enable the ADC to generate DMA requests when conversions are complete. Next, you configure the DMA channel dedicated to this ADC. You set the direction from peripheral, ADC, to memory. You tell it the source address, the ADC's data register, and the destination address, the start of your add-for-aux buffer. You specify the data size, usually a half word for 12-bit or 16-bit ADCs. You set the number of data items to transfer equal to your oversample count, 16 in our case. And crucially, you often enable circular mode for the DMA.
Circular mode.
Yeah, this means once the DMA fills the buffer, transfers 16 items, it automatically wraps around and starts filling from the beginning again on the next transfer request from the ADC. This is perfect for continuous acquisition. Finally, you start the ADC using a DMA-specific start function like HLRC start DMA, passing it the pointer to your buffer and the size.
Okay, it's running. How do you process the data?
The DMA controller will typically generate an interrupt when it completes a full transfer, fills the buffer, and often also when it completes a half transfer, fills half the buffer.
Half and full interrupts. Why half?
The half transfer interrupt, HLIDC con half TPL callback, is useful for reducing latency. You can start processing the first half of the buffer as soon as it's ready, while the DMA continues filling the second half in the background. So you implement those callback functions. HLADC con half CPPLA callback and HLADC con phi PLA callback. Inside these callbacks, you run your averaging routine. You loop through the relevant half of the agra buffer, sum up the values, right shift the sum by the appropriate number of bits, for example, 2 for 16 samples, and store the result in your AGHI value variable.
So the CPU only wakes up briefly when a chunk of data is ready.
Precisely. It processes data in batches, triggered by DMA completion interrupts.
Are there any catches or things to watch out for with DMA oversampling?
A few things. Remember, your effective sample rate is the raw ADC conversion rate divided by your oversample count. The DMA buffer size directly impacts RAM usage, so keep the oversample count as small as you can while still getting the resolution you need. There's still some CPU load from the interrupts, 2 per buffer cycle using half full, but it's way less than per sample interrupts. Memory alignment can sometimes be important for DMA performance check, the Microcontrollers reference manual, and some newer, more advanced microcontrollers actually have hardware oversamplers built right into the ADC peripheral itself. They can do the summing and shifting automatically in hardware, requiring even less CPU work, which is fantastic.
Hardware oversampling. Nice. Okay, one more advanced technique you mentioned, especially for continuous high-speed stuff, this ping-pong buffer idea.
Yes, the double buffer, or ping-pong strategy. This is a classic DMA technique used to maximize throughput and minimize latency when you need to continuously acquire and process ADC data streams without any gaps. It tackles a potential issue with single circular buffers. What happens when the CPU is busy processing the buffer just as the DMA wants to wrap around and overwrite the data the CPU is still reading?
Potential conflict.
Right. Ping pong avoids this by using two separate equal-sized memory buffers. Let's call them buffer A and buffer B.
Two buffers instead of one circular one. How does that work?
The setup is slightly different. DMA is configured to first fill buffer A completely. As soon as buffer A is full, the DMA controller automatically triggers an interrupt, usually the transfer complete interrupt. And critically, it immediately switches its destination pointer to start filling buffer B without pausing.
Seamless switch.
Exactly. That interrupt tells the CPU, okay, buffer A is full and ready for you to process. The CPU can then work on the data in buffer A, safe in the knowledge that DMA is busy writing new incoming data into buffer B.
And when buffer B is full?
When buffer B fills up, the DMA triggers another interrupt and automatically switches back to writing into buffer A, which the CPU should have finished processing by now. That second interrupt tells the CPU buffer B is now ready for processing. The CPU works on buffer B while DMA refills buffer A.
It just bounces back and forth. Ping pong.
Precisely. DMA is always writing to one buffer, while the CPU is always reading from the other, already complete in buffer.
What are the benefits of doing it this way?
The main benefits are no dead time. DMA never has to pause waiting for the CPU, ensuring continuous data acquisition without gaps. Predictable latency. The CPU gets access to fixed-size chunks of data at regular intervals when a buffer fills. Simplified streaming. It makes it much easier to implement real-time processing pipelines where data is constantly flowing in and being processed. Scalability. It scales well for high-speed, continuous data acquisition tasks.
How do you set that up in practice? Is it much harder than circular DMA?
It involves a bit more setup. You need to allocate the two distinct buffers in memory. You still configure the ADC for continuous conversion and DMA requests, but when you initialize the DMA, you use a specific function for multi-buffer or double buffer mode, like ALEMX multi-buffer start in STM32HAL. You provide pointers to both buffer A and buffer B. Then you need to implement the DMA transfer complete callback, ADC convc PLT callback, and potentially the half-complete one too. But now your logic inside the callback needs to know which buffer just finished filling so it can process the correct one. The HAL library often helps manage this state.
So the callback knows if it needs to process A or B?
Yes, essentially. You process the completed buffer while DMA works on the other one.
Any specific considerations for ping pong buffering?
Yeah, similar points as before, but maybe emphasized. Buffer size. Balancing buffer size is key. Larger buffers mean fewer interrupts per second, lower CPU overhead, but introduce more latency between a sample being taken and it being processed. Smaller buffers give lower latency but higher interrupt rates. Synchronization. You need to be careful that the CPU really finishes processing buffer A before DMA wants to start writing to it again. Usually the timing works out if your processing is faster than the buffer fill time, but it's something to consider. Memory. You need twice the buffer memory compared to a single circular buffer of the same effective size. Error handling. Robust error handling is important in case something goes wrong with the DMA or processing falls behind.
Wow, okay. That's a really powerful technique for continuous data flow. What an incredible deep dive. We started with a pretty simple question, didn't we? What exactly is an ADC? And we journeyed all the way through its core concepts: sampling, quantization, resolution, explored the different architectures like SAR and Flash, looked at how it's actually used in microcontrollers with polling, interrupts, and then pushed right into these advanced techniques like oversampling, filtering, DMA, and ping pong buffering that really supercharge performance.
It really does highlight how a component that seems, fairly simple on the surface, the ADC, is just absolutely fundamental to pretty much all modern electronic systems. It's that invisible bridge, isn't it? The silent translator constantly working to allow our digital devices to interact intelligently with the incredibly nuanced, messy, continuous world around us.
Yeah.
I mean, from turning the faintest sound into a crisp digital recording that you can edit or transmit, to precisely measuring tiny temperature changes in a climate control system. The ADC is working tirelessly behind the scenes, just making sense of our analog reality for the digital brain.
So what does this all mean for you listening in? Well, next time you interact with almost any smart device, whether it's your phone detecting the subtle change in capacitance as your finger touches the screen, or a smart thermostat reading the room's precise temperature, or even some complex industrial sensor monitoring critical pressure in a factory, Maybe take just a moment to consider that intricate dance an ADC is performing inside, translating your real world, the physical world, into the usable digital data that drives all this technology.
And maybe, just maybe, you've already used one without even fully realizing its complexity. Perhaps in a simple hobby project you built with an Arduino or a Raspberry Pi, connecting a light sensor or a potentiometer or a temperature sensor to bring your creation to life and allow it to react to its environment. That was an ADC doing the work.